Okay, so first I'd like to say that our collaborators on this project are Marshall University, who are basically on site out in Huntington, West Virginia, as well as URIC, which is the Engineers Research and Development Center with the U.S. Army Corps of Engineers. So they're the ones that are helping us with this project. The research project's primary objective is not only to determine which geophysical technique is most effective at detecting subsurface tunnels within bedrock, but also to determine which one is most logistically feasible with respect to mobilization and deployment in potentially difficult terrain. To accomplish this, a total of 10 boreholes are to be drilled in the vicinity of the first tunnel, which has already been constructed through the bedrock in Huntington. I'll provide some nice pretty maps for you guys in the following slides. 7 of these boreholes are to be uncased and rocked to prevent any interference with data measurements from the probes that we'll be lowering into them. And the remaining 3 will be cased with PVC pipe, which usually doesn't interfere too much depending on what probe we're doing, but some of them do need to be cased, which I'll explain more in depth later. And for those of you who do not know, casing a borehole refers to inserting a pipe into the borehole to prevent structural collapse or outside contamination. Once the boreholes have been completed, our geophysical probes are going to be lowered into them via mechanical winch, after which data collection will begin. Our current plan outlines the installation of sensors in several of the boreholes at roughly 30 feet or 9 meters depth. The geophysical techniques to be tested are shown on the right and include electrical resistivity, magnetics, full waveform acoustic logging and imaging, gamma radiation, fluid temperature and conductivity, as well as seismic measurements. Additionally, there's going to be some additional probes, such as a caliper, to characterize just the general shape of the borehole, but is not integral to the research and the tunnel detection itself. So here's the location. Here's Huntington, West Virginia. We're kind of on the eastern side of the city, and I'll have a more zoomed out map later on. This is the eastern half of the United States. So here's West Virginia, and Huntington is way over there on the west. It's right across the border from Ohio, separated by the Ohio River. So the testing site is known as Muskrat Park. It's university property with Marshall University. And one of the tunnels have already been constructed, and 2 more are planned to be constructed in the future. The one that's been constructed is up here. It's called CF1. The other ones to be constructed in the future is CF2 right here and CF3. EF1 and EF2, that stands for existing facilities, but are not really relevant at this current phase in the project. So here's some geologic background on just the area and what kind of units we expect to encounter over there. The red star over here depicts the location of the test site. Oh, there it is, right here. And then over here is the main town, Huntington, separated from Ohio by the Ohio River, right there. So this I'm showing you a geologic map here from the West Virginia Geologic and Economic Survey's website. This map shows that the topmost layer at our testing site is quaternary alluvium from the Ohio River just to the north. But underlying that, however, is sediment from what is called the Conemaugh Group. This is a Pennsylvanian sedimentary unit primarily composed of siltstone, mudstone, and shale. There is some limestone that kind of lenses in there, but it's definitely not a primary unit that we really expect to encounter at the shallow depths we're going to be drilling to. Overlaying the Conemaugh Group is I always have trouble saying this, Monongahela Formation. So that is overlaying the Conemaugh Group, but we don't have to worry about that too much because up here and down here, that topography is at a higher elevation than where we are right here by about 200 feet or so. So that has since been eroded away, and we are dealing with the Conemaugh Group. The Conemaugh Group is described by the West Virginia Geologic and Economic Survey as being composed of cyclic sequences of red and gray shale, siltstone and sandstone with thin limestones and coals interbedded. It is mostly non-marine and may be divided into the Castleman and Glenshaw formations, which separate marine and non-marine sediments in that unit, but they're not very relevant. But just so you guys have the full story. Monash University also provided us, me and Doug, with rock cores from several preliminary borings that were made at the test site. And my interpretations and logging of those cores are pretty consistent with the Cone Log Group and the West Virginia Survey's description of those units. I'll discuss it more in the next slide, those rock cores specifically. Those borings were drilled to a depth of about 35 to 45 feet and were, like the description says, primarily cyclical layers of sandstone and siltstone. So continuing from the last slide, here are some images of the rock cores that we received from the CF1 testing site. Remember, that was the northernmost one all the way at the top. The top image corresponds to borehole B5 with bedrock cored from about 30 feet to 40 feet. Personally, I'm not really sure as to why coring began so deep down. The other ones that we received were starting around 5 feet, but it still gave us a pretty good sample and an idea of the shale that we can expect to see down there. This particular core sample is actually quite impressive because it's not all broken up, which is kind of uncharacteristic of shale when you're drilling. Usually it tends, depending on the weathering of that shale, kind of to gum up and just essentially get destroyed, which I'll get to in these next ones down here. Those two images correspond to the rock core obtained from boring B3. The borehole was cored from 5 feet to about 32 feet and contains a lot more complex stratigraphy. You have some siltstone right here, transitioning to sandstone, and then that transitions to more siltstone. And then you have shale, and it kind of continues in a cyclical sequence. Here's a big piece of sandstone, this up here. This is top. This is the top of the borehole, and down here is the bottom of the borehole. And it goes in rows, top to bottom, left to right. So sandstone and then shale. And the shale in this boring specifically was just, as you can see, pretty destroyed. It's basically in crumbs and it's all over the place. Here's a map location showing both the tunnel layout from a bird's eye view, a cross section showing how it spans underneath the hill in which it's located, as well as the location of the borings that we plan to drill. The top left image, sorry. The tunnel is comprised of approximately 2 shafts totaling about 235 feet in length and 3 feet in diameter on the southern shaft right there. The upper northeastern shaft is about 6 feet in diameter, and that's the one that's more accessible for people. They're joined by a 6 foot by 6 foot observation room in the center and a vertical shaft connecting that room to the surface. The purpose of having these 2 shafts of differing diameters is to determine the effect of tunnel size on the different methods that we will be implementing. I'll go into more depth later. I have 1 minute, so I should actually probably just skip ahead to that. So here are the different techniques that we're going to be using. I pulled these images. They're not as nice as the ones that Wayne nicely posed for us in his, but we have the ERT, electrical resistivity tomography. I'm not sure. I'm assuming, we're all geophysicists here. We probably all know what that is, but sending electrical signals through the geologic units, measuring their resistivity, and you can kind of determine what kind of unit it is based off of those measurements. Gamma radiation, we're going to be taking measurements of the natural gamma being emitted by the rock down there to see if we can glean any useful information on what's rock and what's tunnel. Full waveform sonic, magnetic susceptibility. Here's the one that Wayne posed for us, which is acoustic imaging. And then we have fluid temperature and conductivity. The plans for the future are to begin mobilizing and getting some real field work done, some boots on the ground by July of this year. We're hoping to complete it not too long afterwards, by around August. And my time is over. But yeah, so thank you. Are there any questions? Is there anyone online that has anything? I'll make sure to include them.
Yeah.
On time or no?
We're, yeah, we're good, and we already